A very important theorem in statistics is the central limit theorem. The central limit theorem states that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size n increases. So you can see how this can be really useful if we can get this requirement met, that then we can approach a normal distribution. As we have a large enough sample size, it doesn't matter what our distribution begins with, the distribution of the sample means we'll approach a normal distribution as the sample size increases. If the sample size is large enough, the distribution of the sample means can be approximated by the normal distribution, even if the original population is not normally distributed. So it's kind of another way to say that. If we have a large enough sample size, then we can use the normal distribution even if our original population is not normally distributed. And by use the normal distribution, I mean use the formulas that we have available to us, the functions on our calculator for the normal distribution, even if the original population is not normally distributed. Okay, when selecting a simple random sample of n subjects from a population with mean mu and standard deviation sigma, here are the rules for the central limit theorem. For a population with any distribution, as long as your sample size is greater than 30, then the sample means will have an approximately normal distribution with mean mu and standard deviation sigma over the square root of n. Okay, so now it's telling us if we have a nice large sample size of n greater than 30, then for any distribution, it doesn't have to be, the original distribution does not have to be normal, but if n is greater than 30, then the sample means will have an approximately normal distribution with mean mu and standard deviation sigma over the square root of n. If n is less than or equal to 30, and we're starting with a normal distribution, so our original population we know is to be normal, then the sample means will have an approximately normal distribution with mean mu and standard deviation sigma over the square root of n. So this is telling us, well, if you have an original population with a normal distribution, then your sample size doesn't matter. You can have a small sample. You're still going to have this condition that the sample means have an approximately normal distribution with mean mu and standard deviation sigma over the square root of n. This is what the central limit theorem says. So that's our second point. The third point says, well, now if you have that small sample size like we did in number 2, but the original population is not normally distributed, then this central limit theorem doesn't apply. So if you've got a small sample and you started with a population that's not normally distributed, then that doesn't fit our central limit theorem, and we won't be able to use the approximately normal distribution with mean mu and standard deviation sigma over the square root of n. Okay, so let's put all this information in a table. Sometimes that helps to see just the key points in a table. All right. So what we were just told now is if our sample size is large or greater than 30, and we have any distribution for our original population, then the distribution of sample means will be the normal distribution, or approximately normal, we'll just say normal. And the mean will be mu, and the standard deviation will be sigma over the square root of n. Okay? Well, another possibility was that we had a small sample, n less than or equal to 30, but we have a normal distribution. Our original population is a normal distribution, and a lot of data we've seen is a normal distribution. Then the distribution of sample means will also be a normal distribution. Whoops. Meant to make a D there, an L there, D. Okay. With mean mu and standard deviation sigma over the square root of n. Okay, and finally, if we have a small sample size and our original population we know is not normal, it could be a uniform distribution or any of the others that we've talked about and many that we haven't, but just not normal, then the central limit theorem, I'm going to abbreviate that, central limit theorem does not apply. And so therefore, here the central limit theorem does not apply. So our check is, look at your sample size first, right? If your sample size is greater than 30, then you're good to go. If your sample size is less than 30, then you want to look at what your original population distribution was. If it's normal, again, continue on with the central limit theorem. However, if you have a small sample size and your original population is not normally distributed, then you won't be able to do the things that we're doing in this section. Okay. So, let's look at some key points having to do with the central limit theorem and the sampling distribution of the sample mean. Given that the random variable x has a distribution, it may or may not be normal, with mean mu and standard deviation sigma, and we have simple random samples of size n. Remember the simple random sample, don't forget about that. We said at the beginning that we were going to be taking simple random samples, not just random sampling, but this specific type of random sampling of size n are selected from the population. So this is what's going on. Let me back this up a little bit. Okay, I'm talking about the central limit theorem and the sampling distribution of the sample mean. So we have this random variable x with some distribution, mean mu, standard deviation sigma. We're taking simple random samples of size n selected from the population. Then here are the conclusions. Now I have to scroll up. The distribution of the sample means x bar will approach the normal distribution as n increases. The means of the sample means is the same as the mean. That should be mean. We only have one mean of the sample means, so let me cross that out. The mean of the sample means is the same as the mean of the population, mu. We saw that because the mean is an unbiased estimator. And the standard deviation of the sample means will be sigma over the square root of n. Finally, let's just look at a little bit of notation here. So, notation for the sampling distribution of the sample mean x bar. So what we'll use is our mean of the sample mean. So we've got this little subscript that tells us it's the mean of the sample means. Well, that's the same thing as the mean of the population, right? The standard deviation of the sample means will be the same as the population standard deviation divided by the square root of the sample size. So this is the mean of the sample means, and this is the standard deviation of the sample means. And it's also known as the standard error of the mean.